In the last session, I explained Introduction to Computational Fluid Dynamics. In this session, I'll be explaining steps in computational fluid dynamic analysis. There are three basic steps followed in computational fluid dynamic analysis. First step is problem identification and pre-processing, which includes defining modeling goals, identifying domain you will model, design and create mesh or grid. Second step is solver execution, which includes setting up numerical model, computer and monitor the solution. Final step is post-processing, which includes examining the results, considering revisions to the model. Pre-processing step includes defining modeling goals, identifying domain you will model, design and creating grid or mesh. Defining your modeling goals include what results are you looking for and how they'll be used, what physical models you need to include in your analysis, what degree of accuracy is required, how quickly do you need the results, do you require any unique modeling capacity. Identifying the domain you will model includes how you will isolate complete physical system, where will the computational domain start and end, what boundary conditions are required, can the given problem be simplified to two dimensions. Design and create grid or mesh includes what type of mesh such as chord or hex, tri or tet or hybrid mesh can be used. For simple geometries, chord or hex mesh are used, which provide high quality solutions compared to tri and tet mesh. For complex geometries, tri and tet mesh provide good numerical solution compared to chord and hex. What degree of grid resolution is required for each region of the domain? Will you use adaptation to add resolution? How many cells are required to solve the given problem? Do you have sufficient computer memory to run the simulation? The solver step includes setting up numerical model and computer solutions. For a given problem, you need to select appropriate physical models like turbulence, combustion, multiphase, etc. Define material properties like fluid, solid or mixture. Describe operating conditions. Describe boundary conditions at all boundary walls. Provide initial solution. Set up solver controls. Monitor solution. CFD calculation. And set up convergence. In computer solutions, the discretized equations are solved iteratively. Number of iterations are usually required to reach converged solution. Convergence is done. Convergence is reached when changes in solution variables from one iteration to the next iteration are negligible. Finally, accurate converged solution is obtained. The final step is post-processing, which includes examining results and considering revisions to the model. The results are examined to review solution and to extract useful engineering data. Visualization is done. Visualization is useful to answer questions such as what is the overall flow pattern? Is there any separation? Are there any shocks or shear layers formed? Are physical models and boundary conditions appropriate? Are there any local convergence problems, etc.? Numerical reporting tools can be used to calculate quantitative results like lift and drag, average heat transfer coefficient. Considering revisions to the model help to answer questions such as are physical models appropriate? Are boundary conditions correct? Is grid adequate, etc. Some of the internet links for popular commercial CFD packages are tabulated as shown in the slide. With this, I will end up this session here. In the next session, I'll be explaining external and internal computational fluid dynamics analysis. Thank you.